Right, this is the continuation of part 3 where we look at influences on vertical wind shear and the background synoptic regime, and we'll focus here on lee cyclogenesis, which is primarily the case in the Great Plains, but we also see this in the lee of the Appalachians or any mountain range. It's capable of happening. Okay, so lee cyclogenesis, when we talk about this, we're primarily interested in what's the direction and orientation of the flow in the mid-troposphere. Typically, the Rocky Mountains or the Appalachians, these are north-south oriented mountain chains, so we're looking for the component of the westerly flow across it. They are coming down the east slopes of the mountains. It warms adiabatically through subsidence warming. That induces a warm core low because it simply think of the analogy of a balloon. You warm the balloon, you lower the density, we lower the pressure of the column or the surface pressure because the column's lighter above the ground. And then you induce pressure falls, and then that changes the wind profile. So you draw mass in the low levels. Oftentimes in the plains, we see the lee trough cyclone deepen well ahead of the big quasi-geostrophic response. So we get a head start on the differential advection and creating that loaded gun profile. And I'd argue that the primary reason that the central and southern Great Plains of the United States is the severe weather capital of the world is simply because we have a warm ocean to the south and southeast, and we have a north-south mountain range at about the right latitude to the west. So we have lapse rate source, moisture source. Any flow across the mountains induces a lee trough, and you get differential advection. So essentially the entire spring, we are trying to create severe storm environments in the central United States. That's almost the default condition. So we'll look at that in a little more detail. Here we look at lee trough formation. This is just a topographic plot. The dark reds and browns, that'd be the high terrain of the Rockies. You notice it's all high terrain out here. The air subsides down the east slope of the Rockies. The highest terrain is in Colorado. So the strongest lee cyclogenesis response tends to be east central and southeast Colorado climatologically. And you can just imagine if you have a deepening low or trough here, lapse rates from the west, moisture from there, you're already setting the stage for a severe storm environment. Now secondarily, we can get the same kind of response to a lesser degree across the Appalachians. It's just the mountains are much shorter compared to the Rockies. So the response itself is lower and weaker in the troposphere. Okay, now here's an example. This one, if anyone recognizes the date, this is the lead up to the Greensburg, Kansas violent tornado. And we'll show you how this lee cyclogenesis process can, and some related changes in the LowLevel jet can help you anticipate potentially a tornado risk that may persist after dark. So here we have the primary synoptic wave from 12Z to 0Z is still located back to the west, just west of the Four Corners, across the Great Basin. There has been some increase downstream of the flow across the high terrain. If you remember, the highest terrain is oriented through here. So we have pretty strong westerly component across the terrain. You would think there would be some kind of lee cyclogenesis response, but it's ahead of the primary synoptic wave. So this is downstream. If you were looking just in QG processes, you'd say, oh, well, the wave's too far west. Nothing's going to happen. Okay, in the low levels, I've just sketched in the red line is the surface warm front, and the brown line is my sad attempt at a dry line. I didn't have the fancy frontal symbols with me. So we have what, as you would see, would be typical of lee cyclogenesis. The cyclone doesn't move a lot. It tends to deepen in place. So I mentioned southeast Colorado. So we have a cyclone that deepens here, but what this has done is it's drawing low-level moisture back to the northwest, and at the same time the gradients are increasing in the lower to middle troposphere. So this is also related with slope terrain and changes in the rate of heating. We can actually get an increase in the low-level jet. So you spend any time out here in the southern plains, you become familiar with the southerly low-level jet. It's very common for this to increase dramatically in the evening. Again, it's related to two primary factors that are tied in with lee cyclogenesis. We've got the diurnal variation of vertical mixing, which the fancy terms, the inertial oscillation, where we have initially deep mixing in the post-dry line, downslope air to the west, and less mixing to the east. And then the pattern actually reverses, and the mixing shuts down in the dry air on the higher terrain after dark. Then the other one we also have that's related to temperature variations over the slope terrain, which is the thermal wind argument. The point here is that if you have gently sloping terrain, this lee cyclone already induces a southerly flow, we can actually get a variation in the low-level jet as mixing shuts down and as it starts to cool more rapidly to the west on the higher terrain. Interesting part about this is with a big ramp up in the low-level jet, if you coincide that with substantial low-level moisture, bad things can happen even after dark. So we'll show an example here. We looked at some significant tornado events in the Great Plains associated with nocturnal low-level jet. At the top, this is just a 3-hour change in the low-level wind speeds. So you can see they go from 15 meters per second, which is about 30 knots, up to about 40 knots. And this is over a few dozen tornado cases. So there is an increase. But if we go over to the right case, these are non-tornadic supercell cases. Low-level jet's maybe a teeny bit weaker, but you see the same kind of mass response. So this low-level jet mass response occurs all the time. The important thing isn't just, is there a low-level jet ramp up? It's what do we have thermodynamically coinciding with that? So it's consistent to see this low-level jet response, and it's very common to see this in strong Lee cyclogenesis cases ahead of the primary synoptic wave by a full 24 hours. If it's moist enough, you have sufficient buoyancy and not too much inhibition, you can actually get an increase in the tornado risk after dark because not only can warm advection increase, but you also increase the vertical shear dramatically in the low levels. And of course, the low-level jet itself is related to the moisture transport. So you can actually bring the moisture into a previously deep mixed environment that doesn't have much convective inhibition, and it's easy to initiate storms. So what happens when you look at these cases? This is an example of, on the left, these two are what happens to the ML Cape at the location where the tornadoes are occurring. And interestingly enough, you would normally think, oh, well, the Cape, it's going from 0Z, which is close to sunset, to 3Z, which would be maybe 10 o'clock Central Daylight Time. The Cape is actually increasing locally. So it's dark, but we are actually increasing the buoyancy. Now, the same thing to a lesser extent you see with the non-tornadic storms. So there's a minor increase in Cape, but a much more dramatic increase and higher values, which is related to richer low-level moisture in the tornado cases. Conversely, convective inhibition increases some. Over here, these are during the evening, it's relatively low. I mean, we are getting thunderstorm development. It increases a little bit. We're taking the absolute value of the convective inhibition, but these are still not huge values. So they increase a little bit, whereas the non-tornadic cases, the inhibition starts off larger and increases to relatively large values. And this can get into other processes related to tornadogenesis, how resistant is the air in the low levels to stretching in the vertical. There's a lot of other stuff we'll talk about later in the supercell tornado portion of these presentations. And here's what happens when you just overlay the soundings. This is a best guess at what was going on in the Greensburg environment. In the background is the purple. This is just over 3 hours. And you see this photograph. There's some structure to it, but if you see the change to the red one, huge increase in the low-level shear. The photograph is expanded, and conversely, the winds here have gone from 25 knots to 40-plus knots. At the same time, the moisture, the purple line on the early sounding, it's increased to the dark green. That's the current. So it's moistened. Even though the temperatures have cooled, the moistening offsets the surface cooling, the buoyancy increases, the vertical shear increases, and you actually go to a more favorable tornado environment. So like in the case of the Greensburg tornado, the tornado was at closer to 10 o'clock or something at night. There were not really any tornadoes in Kansas during the daytime. It was all after dark. Okay, so the Lee cyclogenesis wind summary, you're basically looking for how much flow you can get across the high terrain. The response to the Lee cyclogenesis is even stronger and this is in the QG omega equation, we look at it where static stability is inversely proportional. Low static stability is equivalent to steep lapse rates. So if you've already got steep lapse rates, the vertical motion response is bigger. Slope terrain can also contribute to this low-level jet response in the evening, and if you get the right changes in low-level moisture and temperature structures, you can actually create some fairly serious tornado environments even after dark, well ahead of the synoptic wave.